last time we began graph theory. Any questions till now? So we defined what a graph is. It has vertices, edges. So a vertex has an adjacent vertex, or a vertex is connected to another vertex. A graph is simple if there are no self loops on any vertex. And since if we assume that the edges between a pair of vertices is unique, or at most one, then you can see that the edges can only be quadratic in the number of vertices n. Between a pair of vertices, there could be many edges. In that case, we call it a multigraph. Or the edges can be directed, edges can be weighted. So what are the examples of graphs in real life? So they can model social networks. Where the vertices will be people or members in social media. Members could also be non-people, they can be companies and so on, right? So vertex set is the set of members. And what are edges? Yeah, so edge is the relationship. It can be friend or follow or whatever definition they have. So relationship between members. So for example, if it is friendship, then it will be undirected graph. What is the example of a relationship which will be directed graph? Sorry? Follow or simply, actually, yeah, let's go with follow. But it can also be like, it can be by seniority, who is more senior. Those things will again be directed. Is senior or older, then that also will give a directed graph. Yeah, a closer example to computers is what happens in processes. So how processes are modeled how processes run in a computer. So obviously computers have just a single microprocessor, but there are many processes which execute almost at the same time, right? So something called precedence graph is maintained. So for example, process A can be run only if process B completes. Right? If there are these kind of relationships between processes, then that has to be recorded. you cannot, it doesn't make sense to run A when B is still waiting. So this is called the precedence graph. Right, so precedence graph, the vertices are processes and edges are what should run, what should come before. So in the edge you have u comma v, if say u should run before v. Right, so this again is a directed graph. So in this, if you draw the precedence graph, then what do you learn? Which is the process which should be executed first by the processor? Sorry? Yes, which is in degree 0 or which is the source. So one of the source vertices in the graph should be run first. In fact, all the source vertices should be run first, and after that you should move to the vertex adjacent to the source. Right, and similarly the target vertices should be run the last. So these kind of things you can deduce only if you draw the graph. If you don't define the graph, then you will have no idea how to schedule the processes. So in many cases actually graphs are indispensable. You can't argue properly without drawing a graph. Another such example is class scheduling. So schedule exam for different courses. Where as happens here also, many courses have same students, or intersection is there. Some student is doing 2 courses, so obviously then the 2 courses cannot have the same exam slot. So where courses may have common students. So the question you ask is how many time slots are needed? Right, so if you have a list of courses, each course has registration list. How do you decide the number of minimum time slots that will be required, right? So for this again you have to draw a graph. So the vertices on the graph will be these will be courses, and what are the edges? Exactly. So course 1 and course 2, if there is some common student, minimum one common student, then you draw an edge. Let's start with that. So G equal to V comma E with V the courses, and E will have you will draw an edge from U to V, and it will be an undetected edge if U and V have at least one common student. If the courses are disjoint, then they remain unrelated or unconnected by an edge. Okay, so suppose the graph is a complete graph, which is every vertex is connected to every vertex in this graph, then how many slots are required? Yeah, then, yeah, as many vertices are there, that many slots are required, right? Because no two courses can go to the same slot. Um, so what is the general condition then? Unfortunately, it's very far from that. So let me just say that number of time slots will actually be equal to the, so suppose you think of this as every time slot is a color on a vertex. So you want no two colors to be connected by an edge, right? So it's actually number of colorings, number of colors needed, sorry, not colorings, number of colors needed to color the graph and whenever we say that color a graph by coloring the vertices, what we mean always is that if there is an edge, then the edge endpoint should be colored differently. Okay, this is the definition of coloring in general. So how many colors will be needed, that will be the number of slots also. That's the definition, such that edges, no edge is monochrome. Okay, is this clear? Any questions? So if it was a complete graph, then I mean there was a student in every course, suppose, then in that case the colors required will be number of vertices, that is say n. In all other cases it may be less than n. What exactly it is the number of colors to color the graph. Okay, so this is a new problem in graph theory that you see. So this problem number 2 was also something, this was to do with the topological sort in a graph. Find the source, find the sink and everything in the middle, order it. And this problem number 3 is to do with, it introduces this question of coloring a graph and number of colors needed, minimum number of colors needed. Is that clear? So how do you solve this question? How do you find the minimum number of colors? The colors can be anything, number can be anything, right, from 1 to n. How do you find which one is it? Yeah, wish it was so easy. So this is a very difficult problem. Computationally also it's quite difficult. You can think about it. Another similar practical situation happens when you want to color a map. So color the states in a map, let's say in a map of India. So coloring in a map again has the constraint of what is always meant is that the states which are adjacent, they should not be colored the same, right? They should get different colors. So how many colors are needed to color the map of India? Minimum number of colors. Such that no, oh, you are very fast. So will it remain 4 if India states double or triple in the future, or will this 4 become 8? No. Let's say we stick with 4. Can you always color a map with 4 colors? Yeah, so that counterintuitive thing is actually true, such that no adjacent states get the same color. Okay, so first of all, this question can also be reduced to question number 3. So the graph is, what is the graph? Formally the graph is, every vertex is a state and edge is a edge from U to V if U, V states are adjacent, right? So it will easily reduce to the previous question, but somehow this map coloring question is special, and as pointed out, you can always color using 4 colors or less. This is the 4 color theorem. It ranks in one of the most complicated proofs in mathematics. There are 3-4 such problems, one of which is 4 color theorem. It has a pretty long proof. You can read it if you want. So another problem is obviously highways or roads. So the road network, here it makes sense to have weights, right? You will automatically have weights given by the length of the connection between 2 cities or 2 vertices. So road network is a weighted, and weight is on the edge, not on the vertex. So putting weight on the city will not make sense. Putting weight on the edge is what makes sense there. You can put weight in kilometers or meters. It's a weighted edge. Is it directed or undirected? No, generally it is directed. I mean, at some point there might not be some path may be single way or it may be closed. Generally it's a directed graph. Some sections may be directed. So road network is a weighted edge directed graph. It's clear what the vertices and the edges are and what the weights are. It's obvious from the road structure. The new question of graphs here is that generally what you are interested in road or train network or even for flights network, what you are interested in is the shortest path or shortest distance, right? So given U and V or S and T, what is the shortest distance, shortest path? Shortest distance will give the distance, and then based on that you also want a path. Right, so from source to the target vertices given to you in the input, and the graph of course also given, find the shortest path. So what do you think about this question? How hard is this? I mean, you can even think of the complete graph. Every vertex is connected to every vertex. Paths may be anything, kilometer, distances are given to you in kilometers. How do you find the shortest path from S to T? How many possibilities are there for the shortest path or for paths? Sorry? Yeah, number of connections is way too much. For n vertices, number of connections can be, every place you reach there are n possibilities. So this is like n factorial, right? So if there are 100 cities, already you are up against 2 raised to 100 or 100 raised to 50 or whatever. So this is impossible to actually scan. Although this is a very real problem, but this real problem on a computer suddenly becomes impossible to solve, right? So you need a very clever method, which you will see in algorithm courses. Okay, there are very, very fast, almost linear time algorithms to solve this. But we will not do that today. Okay. So any questions? So let's do more definitions. So what is a subgraph? You can look at subgraphs. V comma E prime of a graph V comma E. So we generally assume that the vertex set is the same, but the edges may be fewer. So E prime, we basically take a subset of E. If this happens, then we say that H is a subgraph. H is a graph, G is a graph, where H is a subgraph of G. It has some properties of G, but maybe not all. If E prime is a subset of E. So obviously the interesting case is some edges. Okay, so some edges of E are may not be there. So that's a subgraph. Degree of a vertex, what is that? So degree of a vertex V in a graph G so usually we assume graph to be undirected, so we just simply say that how many edges are incident on V. That's the degree. Is the number of edges with V. Okay, if it's a directed graph, then there is more terms. Then you have to say out degree to be how many are going out, and in degree to be how many are coming in. But that we don't need for undirected graphs, so we just call it degree. What do you know about the degree? Degree of V is less than equal to? Yeah, we also assume there are no self loops, so there are only V minus 1 possibilities. And obviously it is a number, so it's 0 less than equal to the degree less than equal to V minus 1. So there is this question in assignment 2. So I will not prove this theorem. This theorem says that if you look at the sum of degrees over all the vertices, then it will be did it say that twice the number of edges? Yeah. So if you go over all the vertices, count the degree, then the sum is twice the number of edges. Okay, there is this nice identity. It holds true for any undirected graph with no self loops. And this also implies then that what is the number of vertices with odd degree. Yeah, so if you look at the number of vertices with vertices V with dV odd means in particular it will be positive, but it's only allowed to be 1 or 3 or 5 or so on, then that is even. Do you see this? Because the left hand side sum is odds and then evens, but the right hand side is also even. So even and even you can ignore, and you can deduce that the number of odds then has to be even. Odd is basically 1 and even is 0. So number of ones has to be even. Okay, so there are some graphs which we will use by name. So the first one I have already actually mentioned. So let's see some named graphs. So first example is what is called a complete graph. So complete graph is written Kn, and this is Kn is n vertices, no self loops, but all the other edges are present. Okay, this is the complete graph. So all edges. On vertex set 1 to n. So in this case, what is the degree? Yeah, so this is the example where the degree is maximized for every vertex. Okay, everywhere you see it's n minus 1, and if every vertex has degree n minus 1, can you say about the graph? What are the possibilities? Then it has to be Kn, right? Kn gets characterized by the degrees sequence, and also gets characterized by the number of edges. N choose 2 edges means it has to be complete. Second is path graph. Path graph is just a line actually. So it is just vertex V1 connected to vertex V2 connected to vertex Vn. Okay, so there are n vertices and the edges are n minus 1 in some sequence. Okay, then there is a cycle graph. Called Cn. So here what happens? The same thing as above, but then you also have the ability to go back. Okay, so this is the cycle graph Cn. N vertices, n edges. So what is the degree in a cycle graph for any vertex? Right, so in this case it's 2. If I give you a graph where the degree of any vertex is exactly 2, what can you deduce? How many such graphs are there? Sorry? No, I mean the structure of the graph. Will it always look this way, the way I have drawn? It will, right? It will not. Yeah, you can have many cycles. You may have, for example, just a set of triangles. There also the degree of every vertex is 2. So this doesn't characterize, the degree sequence unfortunately is not enough here. So you can do this as an exercise that for all vertex degree 2 implies that the graph is a union of cycles. Okay, in that case also you have degree 2 for every vertex. What if I say that the degree of every vertex in my graph is 1 or 2? Or at most 2, 0, 1, 2. What do you get then? What is the structure of the graph? Then it's a union of vertices, lines and circles. Okay, so prove these things. This will tell you how complicated a graph will become very soon. Right? You will not be able to pinpoint a graph by just looking at simple properties like degree sequence. Even degree sequence is not enough. So then you have to, you wonder what are the properties which will exactly specify my graph. What are the invariants that are complete? Another example is bipartite graph. So as the name suggests, this will be basically two clusters in the vertices where inside a cluster there is no edge. All the edges go from cluster 1 to cluster 2. Okay, then we say that the graph is bipartite. So V gets partitioned into ST such that H set of the graph is what? S cross T. Okay, so this is just symbolically, it just says this simple fact that there is no edge within S, there is no edge within T, and there are edges possibly going from S to T. Some vertex is in S, some vertex in T. So here you can look at a complete bipartite graph. Which is K m comma n. So this is the graph where you have S of size m, T of size n, and all the edges in the middle, which will be how many edges? M times n. So the edge set here is just edge set of K m n is just m cross n. Okay, the vertex set is disjoint union of m and n. So to make, to formalize the vertex set, you have to say that, let's say the vertices are 1 comma 1 to 1 comma m and 2 comma 1 dot dot 2 comma n. Okay, so these are distinct m plus n vertices, and the edges are only across. Okay. Then there is something called regular graph. So we call G to be D-regular. If the degree of every vertex is exactly D. Okay, so when the degree sequence of the graph is trivial, it is just some number copied that many times. So what is the number of edges in a D-regular graph? On n vertices? This will be? Yeah, so how do you show this? Yeah, use that formula. So that formula will give you the number of edges. It's dn by 2. So now can you draw a graph which is let's say 5 regular on 101 vertices? Why not? Yeah, so this formula tells you that both D and N, I mean one of D or N should be even. If both D and N are odd, then the graph doesn't exist, right? Which is very strange when said in this way, that 5 regular graph on 101 vertices doesn't exist. While on the other hand, 5 regular graph on 100 vertices, will it exist? May or may not exist, right? Go home and draw it. So one thing that is important in algorithms and in implementation of those algorithms is how do you represent your real life problem. So first you will model it as a graph, but then the graph has to be stored in some systematic way for faster query access and whatnot. So what is the representation of graphs for us? Obviously you cannot store it as a picture, right? The graph that we draw as a diagram has no utility in computer science, in implementation. So in implementation you have to store it in a very symbolic way. So what is that? So the data structure for graphs is obviously this, you can store as a 2-dimensional array, or is there some other way? Yeah, or you can store it as a linked list, right, which is many times a better way. So for a vertex I, there will be a linked list which will store all the neighbors of I, right? So you will have the union of these linked lists will only be as much as the number of vertices or edges. Yeah, the sum of the two. So this will be this is a linear representation. And interestingly, this represents the whole graph, right? Because that's all you need. You only need local information. Vertex I, what are the neighbors? Once you have local information, you actually have all the information of all the paths and everything in the graph, right? You don't need anything else. So that is the linked list. So you can have the adjacency list as linked list. That's one way. That is for the implementation. We will look at two other ways which will be to do with matrices. Okay, the matrix representation. That's the two-dimensional array. So first is adjacency matrix. Let me maybe number it. So the adjacency matrix representation is what? What is the I comma jth entry of the matrix? Exactly. So u comma vth entry will be 1 if and only if there is an edge from u to v. So we can call it the adjacency matrix of G. So A sub G for a graph G. This is a matrix where you put a 1 if and only if UV is an edge, and you go over all the UVs. Okay, so this you can see it as a vector or as a matrix, whatever representation you prefer, but it is just saying that as you go over all the edges, in that location you put a 1 if that edge is present, or a 0 if the edge is absent in the graph. This is the edge set of the graph. So the matrix dimension is what? Yeah, it is V cross V, or n vertices, then n cross n. And how many ones are there? How many zeros? Yeah, number of ones is around. If you assume that self loops are absent, then it is twice the number of edges, because in an undirected graph, u comma v and v comma u both contribute. So you have twice, 2 times e many ones, the remaining things are 0. It's a Boolean matrix. So you can store this, but the problem with this in implementation is always that if there were 10,000 vertices, then you have already booked 10,000 square space, right, which is a huge amount of space, and especially in the age of social media and whatnot, the members will be in billions. So if you store that graph as a matrix, then you are talking about billions squared, right? This is even if you have this much of memory space cheaply available, it's very expensive to actually go and access a location in this big matrix. So this is not, you will not use this for implementation. Third is similar, but will look different. That's the incidence matrix. So incidence matrix, I will write, did not give any name. Let's just say A prime G. So what this will do is, so here the matrix was indexed by V cross V, and the entries were 0, 1. Now, in the incidence matrix, what we will do is we will store the function v cross E to 0, 1. Okay, so here basically there is a 1 in the location v comma E, okay, something of this type. So you go over all the vertex edge pairs, which actually will not be a pair, it will become a triple, right, because an edge is itself a pair. So you have a vertex V and then you have, let's say, V1 comma V2, that's an edge. So you go over all the triples, and in that location you put a 1 if the vertex is part of the edge. Is that clear? That's so vertex is incident on the edge, or the edge is incident on the vertex. So it stores that information. Right, so this is an even bigger matrix. It's like n times n square, it's an n cube. But it stores the same information in a different way. The two are actually related. Let me call this M for now. And so you can show that so look at this matrix product, M times M transpose, right? So this is V cross E, E cross V, so the result is V cross V. What do you think is the matrix product value? So what it will do inside is V comma Eth element value, the value at that place times the value at, let's say, E comma V prime place, right? The answer will be 1 if and only if V is incident on E and E is incident on V prime, which means that V and V prime is the edge. So if you work this out, you will get that this is exactly the adjacency matrix. Is that clear? So this incidence matrix actually factorizes your adjacency matrix. You can prove this as an exercise. The other thing is graph isomorphism problem. So generally we are not interested in the specific labels put on the vertices. You can put 1, 2, 3, or you can put A, B, C, or you can put alpha, beta, gamma, whatever. So the labels are not important, right? So the question is, what is important? So every graph has some inherent structure that is important. So to formalize that, we define a relationship between two graphs, which is called an isomorphism. So graphs G and H are called isomorphic if what happens? So first of all, sorry? Yeah, first of all, the vertex set should be there should be a bijection between them. So there exists a bijection tau from the vertex set of G to the vertex set of H, Such that what? Yes, right. So basically the bijection should respect the edge. Every edge should be respected by the bijection, which is to say that whenever you look at an edge u comma v, so you have to be careful here about which vertex you are talking about and which edge. So on the left we talk about G, and on the RHS we talk about H. So if you take an edge in the graph G, u comma v, then exactly, then the kind of the image of this edge should be an edge. Okay, is that enough? Don't you want that any edge in H, its pre-image should also be an edge in G? So we should better put an if and only if here. So let me just say UV is an edge on the left if and only if and then the quantifier you can put here in Vg square. So for any pair of vertices in the graph G, the pair is an edge if and only if the image under tau is an edge. I mean, so if the pair is an edge, then the image is also an edge. If the pair is a non-edge, then the image is also a non-edge, and vice versa. If you can also move from H to G. So then it is now fair to say that G and H are the same graphs for all practical purposes. Just the labeling is different on the vertices, but the connections are all the same across, locally, globally, everywhere. There will be no property difference. Is this clear? This is what the term isomorphism always means for mathematical structures. It will come again when we see more algebra. What do you mean separate points? Isolated points? No. That is all subsumed in this definition. Because if suppose your graph was just isolated vertices, that is captured simply by bijection existence. Bijection is itself, just tau suffices for that. You don't even need the whatever follows in the definition. So you can actually forget about isolated points. So isolated points are not there in the graph G. Whatever you see comes with edges, and then you need this condition to make sense of structure. Any other questions? So let us just see this in a picture. So these are 4 isolated points, or a graph H where you have this, or another graph where you have this, and another graph where you have this. So now what can you say about isomorphisms and non-isomorphisms for this first, second, third, fourth graph? Is the first graph isomorphic to anything? No, right? So this is class 1. Is the second graph isomorphic to anything? Actually, I didn't mean this. I meant this. So is the second graph isomorphic to anything? Yeah, it is isomorphic to the third one, right? Because you can easily just say that I'll map vertex on the top right of the second graph with vertex on the top left of the third graph, and so on. So then you can see that the two are actually same structures. So both of them we can number H2 because they are actually the same structure. I have just drawn it in a different way, but the connectivity information is the same. Now the final graph, is it isomorphic to anything? Yeah, it's not. And the proof of that is, why is there no isomorphism? Yeah, so at the very least, the degree sequence should be the same and the number of edges should be the same. Vertices will be the same because of the bijection. So vertices I have put 4 everywhere, but then it follows from the definition that degree sequence and number of edges should be the same. So this is easily third type of graph, right? Which can also be drawn like this. That's also H3. Okay, so this is how you will, visually you can see whether there is an isomorphism or not. And then mathematically you can write that down. Okay, so so for graph G, you can define a complement graph is the graph with vertices the same, but edge set is what? What will make sense? Yeah, so either you can say that or you can simply say this. Yeah, I put UV if UV is not an edge of G. Okay, so for the graph G, make the edges non-edges. So delete the edge basically. And the non-edges, make them edges, which means draw the edge. Right? So the edge complement gives you what is called the complement graph. And what you should show as an exercise is G and H are isomorphic. So this will be the notation for isomorphism throughout, isomorphism over any object will be denoted with this. So G is isomorphic to H if and only if the complements are. Okay, just you can show this as an easy exercise.